And welcome to this explainer. Today, we're diving into the hidden mechanics of nuclear reactors. We're going to look at real textbook data and basically decode the exact math engineers use to harness the power of the atom. It's kind of like a giant puzzle, and we're going to put the pieces together. Let's jump right into this with a massive paradox straight from our source material. So, if you're thinking about high-energy physics, your gut probably tells you that faster, super-energetic particles would be way better at smashing atoms apart, right? Well, actually, it's the exact opposite. Most modern nuclear reactors literally prefer remarkably slow neutrons over incredibly fast ones. Sounds totally counterintuitive, doesn't it? Let's figure out exactly why. Here's our roadmap for today. 1. The reactor speed paradox. 2. Fissile fuels, no minimum speed. 3. Fertile fuels, high speed needed. 4. The fission to capture ratio. And finally, 5. Choosing the right fuel. Section 1. The reactor speed paradox. Okay, so according to the text we're breaking down today, it is a stated, hard fact that fission probabilities in a slow neutron reactor are actually higher than in a fast neutron reactor. And this isn't just some minor technical footnote. The source explicitly points out that this specific advantage is exactly why most present-day reactors are built to use slow neutrons. Slower speeds literally give them the edge. But to really grasp the sheer scale of this, we've got to look at something called cross-sections. Just as a quick refresher, a cross-section, which is measured in a unit called barns on the graphs we're about to see, simply represents a probability. Think of it like a target. A larger cross-section means you have a much higher probability of that atom splitting or undergoing fission. Section 2. Fissile fuels. No minimum speed. All right, so here we have our two teams of nuclides, pulled straight from the source text. On the top row, we've got the fissile team. That's uranium-233, uranium-235, and plutonium-239. Now, check out their threshold requirement. It's 0, none whatsoever. But then look at the bottom row. This is the fertile team, including uranium-238 and thorium-232. They behave completely differently and have a very strict, incredibly high threshold right around 1 MeV. Keep these two teams in the back of your mind, because we're going to look at the fissile team's data first. So, checking out figure 2.5 from the text, we can see the actual data mapped out for those fissile fuels. The bottom axis tracks the energy of the neutron in electron volts, and that vertical axis, that's our cross-section, our probability of fission. Now, the absolute crucial detail is right here on the far left. Look at where those lines start in the sub-eV range. That's the super, super slow energy zone. Those lines are incredibly high up. For fissile nuclides like uranium-235, there is absolutely zero threshold required to kick off the reaction. In fact, their probabilities for fission are literal orders of magnitude higher at these crawling sub-eV speeds than they are way over on the right side at the super-fast mega-V speeds. It's a massive, massive advantage for slow neutrons. But you probably also noticed that the middle of this graph looks totally chaotic. The text identifies this incredibly jagged area as having many resonances in the intermediate range. Basically, as the neutron speeds up past that slow phase, the probability doesn't just drop off nice and smooth. It violently spikes up and down. It's highly unpredictable. And really, that's just another reason why engineers prefer the stable, remarkably high probabilities down in that smooth, super slow sub-eV range. Section 3. Fertile fuels. High speed needed. Now we're looking at figure 2.6. This shows our fertile nuclides, uranium-238 and thorium-232. And wow, just at a quick glance, you can immediately tell this is a completely different story from the last graph. Let's trace this line starting from the left again. Over on the far left, at those slow sub-eV speeds, the line is basically on the floor. The source notes that for fertile nuclides, these low-energy cross-sections, even with those tiny little resonant spikes you see, are sub-threshold and just extremely low. Honestly, they're so low, they're often considered totally insignificant. For fertile fuels, you just hit a massive brick wall until you reach that strict threshold close to 1 MeV. You absolutely, fundamentally need fast neutrons to get any meaningful fission probability out of these guys. So, when we put these two realities side by side, the whole paradox completely unravels. If you're running fissile fuels, you get incredibly high probabilities of fission at incredibly slow speeds. But with fertile fuels, those same slow speeds give you practically nothing. You're forced to crank it up and use fast, high-energy neutrons. And since getting super high fission probabilities at lower energy costs is exactly what you want, the slow neutron approach with fissile material naturally became the gold standard in historical and modern reactor design.
Section 4. The fission-to-capture ratio.
Now here is the big plot twist. The choice of fuel is not just based on fission probabilities alone. Our text clearly states, and I quote, "Competition with the capture is essential to be considered." So what does that actually mean? Well, think of it as an atomic tug of war happening right inside the reactor. When a neutron hits an atom, it doesn't always magically split it. Sometimes the atom just absorbs the neutron like a giant sponge. We call that capture. If a neutron gets captured, it's basically a dud. It's completely lost the reaction. So engineers aren't just trying to trigger fission. They are constantly fighting this competition. They need the probability of fission to heavily, heavily outweigh the probability of mere capture.
Section 5. Choosing the right fuel.
Our source outlines a really clear, logical flow that helps engineers make their preliminary choice for nuclear fuel. Step 1, they analyze those cross-section graphs to figure out the sheer fission probabilities at different speeds. Step 2, they evaluate the competition, calculating that absolutely vital fission-to-capture ratio. And finally, step 3, armed with both the probability and the efficiency data, they can make a highly informed, perfectly calculated choice for the reactor. All right, let's summarize what we've discovered today. We started with a total paradox and we cracked it. We now know that, surprisingly, slow neutrons yield orders of magnitude higher fission probabilities in fissile fuels. We also saw that present-day reactors are designed specifically to leverage this slow, sub-MeV edge. But perhaps most importantly, we learned that just looking at a single metric isn't nearly enough. The ultimate design decision always relies on mastering that delicate balance of the fission-to-capture ratio. It really makes you appreciate the immense, microscopic tug-of-war that is literally powering our modern world, doesn't it? As we push the boundaries of physics and explore advanced reactor designs, you've got to wonder, if the future of clean energy relies on mastering this delicate atomic balancing act, what incredible new fuels and combinations might we unlock next? Thanks so much for hanging out with me on this explainer, and keep asking those big questions.